Hi, this is an example problem from Chapter 26 on correcting nearsightedness, which means you can't see far. Pause for a moment to read the question. Okay, so for this problem, we are going to need to use a lens to correct problem with a person who can't see objects that are far away. And so in this case, what we're interested in is the person's far point. Let's quickly look and see from the PDF notes what this means. So again, accommodation range, that's the range of distances where you are able to see objects and form clear images. The far point is the furthest point where you can create a clear image on your retina. And for the average, for the normal eye, the far point should be infinitely far away. If it's less than that, we can correct it. What do we need to do? Well, the problem with something being far away is the rays are really parallel, and we need to relax our eye as much as possible so they don't bend very much. Well, if you can't relax it enough, or it's incapable, you're not going to have your image hit the retina. So we need to have less convergence. We don't want it to converge so soon. We're going to put a diverging lens in, and that's going to correct so that the image goes to the back of the retina. Now, how do we think about this though? Well, what we think about is, for a distant object, the lens is going to produce a virtual image at the far point. That's where the person's eye can see. So you put the virtual image at the far point, and then you can see it effectively. So how do we do that? Well, first we're going to go ahead and start like we always do with corrective lenses. So we're going to start just by drawing the principal optical axis. Get a little straighter one there. There we go. And we're going to go ahead and draw the eyeball. Here's our eyeball. And there is our pupil. Funny looking eyeball, I must say. All right, and we're going to go ahead and just label some points here now. So starting with the eyeball here at this position, we know that we have a far point of 80 centimeters. So let's go over here and say, okay, here's the far point. And the distance here, that is 80 centimeters from the eye. All right, now that's where the image is going to go. We want the image to appear at the far point. That's where that person can see it. But where should the object be? If we want to be able to see things as an average person, the object should be way over here. The object is at infinity, so it's way the heck over here, right? Now, we've gotten the important points drawn out. Now we need to figure out where we put the lens. For this one, it's a contact lens. It goes right on the eyeball. And this is a diverging lens, so kind of draw it in this hourglass shape, right? There's your diverging lens. What's important, again, is the center of the lens so that we can measure distances, and that coincides with the eye for contact lenses. So to measure out to the image, it's going to be like that. So DI, we can see it's going to be 80 centimeters. And we again need to ask about sign conventions. Well, the object is on the same side as the image. And again, like we saw previously, this is a negative sign. It's a virtual image. Now to do the object, well, that one's going to be kind of easy. How do we do this? Well, let's start from the lens. And you just go out. You go out forever. You go out to infinity. It keeps on going. And so DO is equal to infinity, or plus infinity if you want. Now we can go ahead and use this information to calculate the focal length in part A as we use the thin lens equation. 1 over f is equal to 1 over DO plus 1 over DI. Put in our values, 1 divided by infinity for the object plus 1 divided by a negative 80 centimeters. Now 1 divided by infinity, we know that this whole term is going to go to 0, which helps us a bit. And so we can simplify this. F is going to be equal to minus 80 centimeters, just taking the reciprocal of both sides of the equation. And so that is the focal length for the contact lens to be able to correct this person's nearsightedness so that they can see something that's infinitely far away. Part B, we're going to go ahead and calculate the power. Again, the optical power, nothing to do with watts here. This is diopters. And we need to take the reciprocal of the focal length, got to be in meters. So we're going to have 1 divided by negative 0.8 meters, which gives us a value of negative 1.25 diopters, which we remember are equal to inverse meters. And that's the optical power of this diverging lens that corrects the vision of a nearsighted person. Notice that the negative sign tells us that it's a diverging lens. That's what the sign conventions are for diverging lenses. They're negative for the focal length and for the power. And the 1.25 tells us the strength of that lens. Again, stronger lenses have shorter focal lengths, so when you take the reciprocal of a small number, you get a bigger number of diopters. The higher the value is for the diopters, the stronger the strength of that lens, the quicker it is able to converge parallel rays.